Hello, I'm Pavel, and today I want to talk about gambling. Not a good topic? Yeah, probably we should consider some more appropriated stuff like, I don't know, climate change or whatever. But the modern probability theory is supposed to originate from a dispute between two famous French mathematicians somewhere in the middle of 17th century. And they spoke exactly about gambling. So maybe it's not as shaming topic. Go on. Consider a simplest fair game where you have 50% chances to win and 50% chances to lose. Side comment. Actually, mathematicians prefer to express probability in numbers from 0 to 1. Well, game could be anything. It could be dice rolling or coin toss, doesn't matter. And if you play only once, there are only two possibilities, whether you win or you lose. Very simple. It is more complicated if we play several times. Here to predict the final result, we will follow so-called frequentist approach. Just consider all possible combinations, maybe write it in the form of table, then sum up the combinations which lead to the same outcome. In this particular case of 2 rounds, we can conclude that in half of cases we win just nothing, in quarter of cases we win €2, and in quarter of cases we lose €2. We can continue this way for 3 rounds. The table becomes a bit more complicated, but we can use the previous table as a block. I outlined this block in red. And after summing everything up, we get the probability distribution. 4 rounds, we do the same thing. Each combination is a building block, and we try to build some kind of pillars out of them. Probability pillars. I think this, or approximately this way, the noble gamblers of 17th century tried to analyze their game. But you see that the number of possible combinations increases dramatically with number of rounds. Very soon, building such probability pillars becomes undoable work. And here, famous mathematicians are going to help. Some of them, definitely Cardano, were also passionate gamblers. First of all, we have to extend the definition of variables. You know, a simple algebraic variable points to a fixed number. And also functional relations between them are fixed. For instance, if y is x squared and x equals 2, then y is nothing but 4. Random variables are different. They appear in certain range, and each value in this range is assigned to a certain probability. It could be a discrete range or continuous range. The only condition is that the sum over all possibilities or the integral over all available range should be 1, because something should definitely happen with probability 1. Also, functional relations are modified. For instance, if the random variable x is equally distributed in the range from 0 to 2, then the random variable y, which is square of x, is distributed in the range from 0 to 4, unequally distributed like shown in this figure. First of all, we will need Bernoulli distribution. That is just a random variable which takes the value 1, means success, with probability pi, and it takes value 0, which means failure, with the rest probability. Let's do that many times and pose the following question. How many times we expect in average to succeed from a large number of trials? N small successes from N large trials. And that is a so-called binomial distribution, which is expressed with this formula, quite complicated with factorials. And this formula is exactly what we need to build our probability pillars. In particular, for fair games, if we know that the probability of success is exactly 1/2, the binomial distribution looks like that. Very good. But binomial distribution is a bit complicated for calculation and for understanding. Fortunately, at large number of trials, it converges to the so-called normal distribution or Gaussian distribution. And this Gaussian curve is quite well known even by very far from sight people. The Gaussian curve has actually only two parameters, the middle point and the parameter sigma, which is called standard deviation. And this sigma defines the width, the spread of the Gaussian function. Both middle point and standard deviation for Gaussian are quite easy to calculate. For 50-50 games, middle point is just enlarged by 2, and sigma, standard deviation, is 1/2 of square root of enlarge. Now we are going to convert this abstract mathematical curve into understandable probability pillars expressed in terms of cash. First of all, we have to rescale it. With each success, we take 2 euros from the table. Thus, we have to multiply the horizontal scale by 2 euros. But to participate in each round, we have to pay 1 euro. So we must shift the curve n euro to the left. So this is our final probability gain-loss curve. It's interesting to investigate how the spread of probability, the width of probability function, depends on the number of rounds, n. This formula suggests that it increases as a square root of n. Let's plot the distribution for 10 rounds. In fact, for 10 rounds, we have to use the discrete binomial distribution, but just believe me that it looks like that. 100 euros. Now we can safely use the continuous Gaussian distribution, and its standard variation will be 10 euros. Larger than in the previous case, but if we plot it in the complete range, plus minus 100 euros, it will look narrow. Well, theoretically you can win 100 euros, but the actual probability would be quite small. Most probably you will end up with something like plus minus 10 euros. 1000 rounds. Although the standard deviation increase is still 32 euro, it's nothing comparing to 1000 euro you might naively expect to win. I mean, the chances to win 1000 times from 1000 is not zero, but this is microscopically small. It never happens. And this simple truth was many times confirmed by prisoners who conducted a very long game in prison, and they say there is no fun. No fun to roll dice 1000 times and to win 30 euro or to lose 30 euro at the end. If we are looking for fun, maybe to visit a casino, for instance, Kurhaus in Baden-Baden. I have been once. It's fantastic. Very authentic atmosphere of the 19th century. It's pleasure to join respectable ladies and gentlemen at the roulette table. Okay, now we are well prepared to consider a roulette game. For those who don't know the rules, I will quickly explain that. Let's look at what is called European roulette. There is a table, a field separated onto the numbered sectors, numbers from 1 to 36 plus 0 sector. On top of that, there is a roulette wheel with numbered pockets, 36 numbers plus 0, and every time the wheel is turned, the ball ends up in one of the numbered sectors. There is also American roulette, and the only difference is that there are 2 zeros in this variant. Actually, the difference is not geographical. You can meet American roulette quite often also here in Europe. The difference is rather in the degree of greediness of the playhouse owners. Well, and you can make bets. For instance, you bet that an even number will win, and you put €1 onto the even field. The roulette functions like somebody else put the virtual bet on the complementary field, in this case, the odd field. And if you win, you take your money back plus all complementary fields. In this case, you take €2 from the table and your payout is 1-to-1. To make game a bit more funny, each number is associated to the color, red or black, and you can bet on color. For instance, if you bet €1 on red, it means that one virtual euro is put on black, and if you win, you get €2 from the table. So the payout is again 1-to-1. You can bet also on dozens. For instance, if you bet on the second dozen, the numbers from 13 till 24, it means that there are virtual bets on the complementary dozens. And if you win, you take €3 from the table. Your payout is 2-to-1. Another kind of bet. You can bet on two numbers, so-called split. For instance, you put €1 on the field just in between numbers 9 and 12. It means again that there are complementary virtual bets on the other combinations. And if you win, if 9 or 12 is on the wheel, you get €18 from the table. Your payout is 17-to-1. And the most ultimate bet. You put on a singular number. For instance, you bet on the number 12. And if 12 wins, you get €36 from the table. Your payout is 35-to-1. Now I will be back to the site you probably already saw at the title of the presentation. One hero of the Jack London story says that roulette itself is the system, and there are no other systems that can beat it. Well, I will not retell you the story, please read it if you still didn't. I'll just mention that generally this statement is correct. But does it mean that we should make our bets chaotically without any systems? I don't think so. And my arguments are following. I know there are certainly some very bad systems. For instance, if you put the same bets simultaneously on red and black, you are guaranteed to win nothing. But if the ball stops at 0, you will lose all your bets. Another example of very bad system. You can check that for each happen number from 1 to 36, you will win nothing. But if the ball stops at 0, you will lose all your bets. Well, if there are ultimately very bad systems, it means that another better systems are possible, right? Now let's employ knowledge gained from the consideration of the coin toss. Suppose that we have a budget €100 and we want to divide it on 100 bets, and we always bet on two possibilities, red or black. Well, we calculate the Gaussian distribution and its standard deviation is 5. As before, we multiply the scale on €2 because we take 2 euros from the table every time we win, and we must subtract 100 euros because every time we should put 1 euro on red or black. And here is our prediction curve. So with such game strategy, at the end we will win or lose something like 10 euros. Let's change the strategy. Let's divide our budget on 10 bets, each of 10 euros, and do the same calculations. Finally, you see that your spread of possibilities is much larger. At the end, you most probably will win or lose something like 30 euros. To my mind, it's more exciting than the previous strategy. Or we can put all 100 euros in one bet. Then you either win 100 euros or you lose 100 euros. Also not bad. But to my mind, there is no joy in such strategy. Everything will be finished too quickly. If we want to enjoy, let's go back to 1 euro bet, 100 rounds, but put the bet on single number. We can calculate the Gaussian distribution with this standard deviation. We multiply the scale on 36 euros. That's what we get from the table if we win. We deduct 100 euros. That's what we pay to participate in rounds. And here is our final probability curve. Most probably at the end we will win or we lose about 60 euros. But there is also small but real chance to win much more than 100 euros or to lose much more than 100 euros. I think not bad strategy. Something is forgotten? Of course. We forgot about the interest of playhouse, so-called playhouse edge. We forgot about the existence of the great and horrible zero. And if zero happens, neither red nor black wins. Okay, let's recalculate our first strategy with taking into account zero. It will slightly change, namely the spread of probability curve would stay almost same, but the average value, the mean value, will slightly shift to the negative region. It will be minus 2.7. It means that for each 100 euros in play, you will in average lose 2.7 in favor of playhouse. Recalculate the second strategy. We will find exactly same negative bias, 2.7 euro, in our final probability curve. The third strategy. The existence of zero will make our chances to win and to lose slightly unequal, and calculation shows that the average win will be again this verdammt minus 2.7 euro. And our best strategy, 100 bets on singular number, will also suffer from the same negative bias. But the good message is the standard deviation, say the spread of your results, will be still significantly high. I would say most probably at the end you will win something like 55 euros or you will lose something like 60 euros. Yeah, it's still not bad, provided, I stress, provided that you play 100 times, not more. To resume, your average win in roulette will be always negative. It means that in average you will always lose. And that is independent on your playing strategy. We can show that a bad system results in exactly same negative bias as a good system. It only depends on the type of roulette. We can calculate that for American roulette, this negative bias is twice higher. What you can affect are the limits of your final win or loss. With a bad system, your maximal win will be just 0, and with a single number bet, the maximal limit will be large. But of course, it's only hypothetical. In reality, the chances are very small. Okay, these limits are independent on the type of roulette. European, American are the same. And the most important thing we can control is the deviation from the average result. This deviation is rather small for bets red versus black or odd versus even, but it's rather high for a single number bet. So, this deviation is your chance to leave the playhouse as a winner. You know the average is negative, you lose. But with high deviation, there is a chance that you will deviate from this negative average towards a positive value. And of course, there is a chance that you will deviate to the negative side. But that is a game. Just as an exercise, we can also calculate the standard deviation for the bet system I showed you previously, and we will find that it doesn't depend on the number of rounds. Okay, I'm not sure that somebody is going to check experimentally these distributions in real casino, but this example smoothly drives us to the final words of the presentation. I guess that after deep analyzing the gambling games, they suddenly appear quite boring. But analyzing the gambling probabilities itself is quite exciting, isn't it? Okay, I wish you a good luck, and not only in gambling,